Space shingles, casting bespoke connectors for structural shingles. Introduction. My name is Becker and I'm presenting the paper Space Shingles at the AAG 2020-21 on behalf of the team. The work is a collaboration of the Chair for Structural Design at the University of Applied Sciences Wismar, Professor Fromm, co-authored with Florence Keller, and the Chair of Digital Methods and Architecture at the Leibniz University Hannover, headed by myself and co-authored by Mecke. Some of you might have attended the workshop here at AAG, Collaborative Choreographies, Discrete Design in VR, by Jan-Philipp Drude, also researcher at our institute DMA. We share a long-standing interest in utilizing 3D printed components in hybrid material assemblies for architectural and structural applications. This includes tube connectors for space frame-like structures, plate connectors for folded plate structures, and hybrid plate tube connectors. The work on space shingles is motivated by further investigating plate connectors joining a double-layered structure without the need for structural framing and still providing a substantial structural depth. Abstract. We describe how established manufacturing methods and certified materials in metal casting are used in conjunction with 3D printed molds for creating geometrically complex structural aluminum connectors. We propose a novel connector that differs from bespoke tube connectors and traditional spider fittings. We showcase a connector for joining sheet material to form larger double-layered structural assemblies such as decks, shells, without the need of any substructure. The connectors are produced indirectly using a large format binder jet 3D sand printer for casting metal cores. It results in bespoke cast metal connectors with approved material properties. Shingle structures have been around for thousands of years. They have the advantage of taking up tolerances much better than any other system. Modern interpretations of shingles are the 300-meter high-rise facade for the Bishopsgate Tower by KPF, the Serpentine Pavilion Carpet of Stone by Ishigami, or the ETH Pavilion 2017 by Grommat-Kohler. These loose-fit properties of shingle structures make them specifically suitable for novel recycling strategies in the context of computational design, as they don't rely on zero tolerance and thus offer scope for combinatorial optimization and form-finding strategies. These higher tolerances also offer more possibilities for local node optimization. Introduction. Problem definition. Current methods of direct additive manufacturing metal are direct metal laser sintering, direct metal laser melting, 3D printing with gas metal arc welding. None of these three methods have already impacted architectural design and the construction industry yet. The only additive metal manufacturing process applied at architectural scale is via arc additive manufacturing, with projects like the robotically printed bridge by MX3D. Today, the process of metal casting with sand molds is governed by codes and certified methods in many industries. There is no significant difference in the performance of traditionally cast metal parts and parts cast in 3D printed sand molds. There are some geometric limitations when casting and using casting processes. These molds also require runner and riser and gating for the liquid metal to flow into all cavities and vent the remaining air. The knowledge gap. Complex architectural metal products such as spider fittings have been traditionally fabricated using processes such as investment casting or sand casting. A key project using 3D printed sand molds for metal joints is Digital Metal Shaping Liquid Pavilion by My Body and Dillenburger at ETH. The project demonstrates the use of 3D printed sand molds to cast variable space frame tube connectors. Our project builds on the findings by My Body and Dillenburger. It goes further by exploring a new connector type which links plate elements directly and thus forming a structural architectural surface without a supporting frame. This unconventional structure conventional structure system will be referred to as space shingles. It has similarities to a space frame without the hierarchy between load-bearing and cladding elements. Objective. The connectors which link the shingles to a functional structure as well as providing architectural surface have a fair bit of geometric variation in order to reach the panels. They also offer the possibility to be topologically optimized for local varying loads. Methods. A proof of concept prototype is forming the base for a full-scale architectural demonstrator at a larger stage. Such a space shingle structure could act structurally as a truss, shell, or any hybrid in between. Proof of concept. Fabrication pipeline. Today, 3D design models can be evaluated for their structural performance almost in real time and thus be topologically optimized for minimal material use. The connector described in this paper is fabricated using two forming processes: 3D printed molds and metal casting. During the first step, a high-resolution sand mold is 3D printed directly off the digital model. This is done on a Voxeljet VXC 800 with a continuous resolution of 400 dpi and a layer thickness of 0.2 millimeters. Such a printer with continuous endless print bed would allow for industrial production. The prototype connectors are around 140 millimeters cubed in size. The cured half molds are properly cleaned of any loose sand. Therefore, it is necessary to have each mold designed in two halves. These half molds also include a runner riser gating system for the liquid to flow easily and fittings to connect the two halves precisely together. Once the two halves are joined, a liquid aluminum alloy is cast into the mold. This forming process allows to fabricate complex and intricate parts to high precision. Design pipeline. The overall geometry of the prototype was chosen to have a meaningful test context for connector variation, structural conditions, and difference in connection details. The shell-like structure exhibits enough curvature to be structurally significant. It is still shallow enough to experience some moment forces which have to be taken up by the structural depth provided by the height of the connectors. The prototype consists of 144 panels, each around 800 millimeters and 10 millimeter thickness, 60 connectors with an average height of 140 millimeters. The geometry model was defined as a lightweight parametric representation in Grasshopper 3D, consisting of planar quad surfaces and centerline geometry for the connector. The panels have a tolerance zone which can take up 10% of the panel size, while still providing enough overlap for shingles to work as a rain screen. The local geometric range of connectors in terms of centerline length and angles from the base for developing the bounding volume topologically via a form optimization process in Autodesk Fusion 360. The viability of the connectors' contact surfaces to the panels was ensured. Positions for the threaded drill holes identified. The two parted molds for each connector was generated in line along with a system of runner riser and gating. The contact surfaces are machined for planarity and the threaded holes are cut at the marked position. Engineering. The main principle of the proposed structural system is a spatial truss where the top and bottom chord are made up of plates linked by bending resistant connectors providing the necessary spacing for the required structural depth. The overall form is analyzed under dead loads for displacement. Based on the simulation, the heights of the connectors are adapted when necessary to compensate over and under performance. In a second optimization pass, the load conditions at the connection points of each connector are taken into consideration for topology optimization. Integrated design and optimization. The design integration system was developed to control the overall geometry and providing the constraining information for developing the connector topology. Different initial volume geometries were tested as shown, and resulting connector topologies cleaned up geometrically and improved for 3D printing and metal casting constraints. Evaluation. Overall, the system of space shingles shows great potential to be further developed with such a bespoke metal cast connector. The fabrication process proved to fall into the tolerances as expected of well-tested industrial processes. Further destructive examination of the connector should be performed. These should be done in conjunction with a thorough prototyping design development of the connection detail between connector and plate. Since handing in the paper, we are working with students on a larger demonstrator of space shingle structures and their architectural design potential. Discussion. Outlook and impact of findings. The development so far seems very promising for feasible applications of metal cast connectors from 3D printed sand molds in architectural context. The design of an overlapping loose-fit shingle takes out a significant degree of complexity in the manufacturing of the panels, as it eliminates any plate-to-plate timber joint and allows for panel size tolerance in the margin of up to 10% in length. Further developments. The connections of details between metal connector and shingle plate should be further tested and developed. Also should the design process be further developed to harness the potential of material reuse and recycling. A larger architectural demonstrator would also address architectural questions such as integrating architectural elements, daylight, and environmental performance, as well as human comfort. Products and applications. As metal casting is a well-established process, and so is the fabrication of 3D printed sand molds, one can expect to bring such products fast to real projects in the building industry. We also see applications for processes which already consider 3D printing as a strategy, but lack the high strength characteristics of certified materials. It is up to designers and engineers to develop meaningful architectural products, which go even beyond the potential of a highly variable, materially minimizing product presented here today. Thank you very much, and I'm looking forward for questions on the forum in any other form.